In this video, we're going to state some criteria for differentiability of functions of several variables. So suppose that you have an open set A in Rm, and you have a function f from A to Rn. Let's just recall that when you have a function from A to Rn, then the output is going to have n components, and the function that takes x1 through xm, this point in A, to the ith component, that's called the ith component of f, and that's denoted f sub I. So f sub 1 is the function that takes x1 to xm to the first component of f, and so on. So you have these functions f sub I. And the theorem says that suppose that the partial derivatives, all the partial derivatives of the component functions of f exist at each point of A and are continuous. So the partial derivatives are all continuous. Then f is differentiable at each point of A. Okay? So in particular, if you take n equals 1, then you just have a real valued function, and this is just the partial derivatives of f. So if you have a real valued function f from an open set in Rm into the real numbers, it's going to have m partial derivatives, right? And if those partial derivatives are continuous on the domain of f, then the function f is differentiable. And a function that satisfies the conditions of the theorem, so this is a function where the partial derivatives of the component functions of f exist and are continuous on A, such functions f are called continuously differentiable, or C1. So for instance, if you take n equals 1, then you have a function like, let's say m is 2, say, then you could have a function f of xy equals x squared y minus sine of x y cubed, or something. If you take the partial derivatives, you see that they're continuous functions, and so f is differentiable. This function is differentiable by the theorem. So this is a very useful fact. I mean, in practice, you're not going to see lots of functions that are not differentiable, right? You're not going to see many functions where the partial derivatives are not continuous. I mean, we know that just having the partial derivatives exist doesn't guarantee that the function is differentiable. So the theorem says that if the partial derivatives are also continuous, they don't just exist, but they're continuous, then f is differentiable. And we're rarely going to see a case where the partial derivatives exist, but are somehow not continuous. Of course, this is a criterion that implies differentiability. So there could be functions that are differentiable, but the partial derivatives are not continuous. I mean, this is just a sufficient condition. It's not necessary. But most functions that you'll see will be C1. Okay. So C1, continuously differentiable, implies differentiable. That's what the theorem says. Okay. And the proof is in Munkris's book. It's fairly long, and we're not going to go over the proof. Now, when you have a function from a to Rn like this, it's going to have partial derivatives, right? And those partial derivatives themselves are going to have partial derivatives. Because if you have a function from a to Rn, the partial derivatives will also be functions from a to Rn. Well, I should clarify that so we're done with the discussion of this theorem. So the partial derivatives, d sub j fi, these are functions from a into R, right? Because fi is a function from a to R. The partial derivatives are functions from a to R. So these will also have partial derivatives. So you can have, the kth partial derivative of the jth partial derivative of fi, for instance. So these are called the second order partial derivatives. And of course, those second order partial derivatives themselves will have partial derivatives, just like when you have a function of one variable, right? You can have the first derivative, second derivative, third derivative. When you have functions like this, they're going to have first order partial derivatives, and then those partial derivatives are going to also have partial derivatives, so that gives you second order partial derivatives, then you get third order partial derivatives, and so on. And if you have a function from say from R3 to R, okay, if you have a function from R3 to R, then that's going to have three partial derivatives. And then each of those three partial derivatives will have three partial derivatives. So there will be 9 second order partial derivatives, right? And then each of those 9 second order partial derivatives will have three partial derivatives. So then you're going to get 27 third order partial derivatives, and so on. But the nice thing, and then before going on, maybe we should define what CR means. So Munkris defines this notion of CR, and it just means that the partial derivatives up through order R are continuous. So if all partial derivatives up through order R are continuous, then F is called of class CR. And we say that F is of class C infinity if the partial derivatives of all orders are continuous. And in this series of videos, we're basically going to only work with C infinity functions. But most of the theorems will not require that the function be, have all the partial derivatives be continuous, right? Because most of the time you will not need to consider the 100th order partial derivative. But somehow it's often just assumed that your function is C infinity. And many books do assume that when they're working with differentiable functions, they just are working with C infinity functions. Okay. I don't think it's worth making a big deal out of the CR and C infinity. Okay, but so the point I'm trying to make is that this CR, if you assume that a function is, CR and not necessarily C infinity, then it strengthens the statement of the theorem. I mean, C infinity is a stronger condition. So if you have a function and you prove a theorem about functions that are of class, C2, but not necessarily C infinity, then that's a more general statement. But in reality, it's just not a big deal for the purpose of just explaining the general concept. Okay. And as you might expect from your experience with multivariable calculus, it doesn't matter in most cases the order in which you take the partial derivative. So if you take the first partial derivative and then the second partial derivative of that, then you end up getting the same as taking the second partial derivative and then taking the first partial derivative of that partial derivative. Right? This is something that we're used to. So for instance, if you have something like f of xy equals, say, x squared y cubed plus sine of xy squared, I'm just making this up, if you do the partial derivative with respect to x, then you're going to get 2xy cubed plus cosine of xy squared times y squared. And then if you take f sub xy, oh, why did I make this example so complicated? If you take f sub xy, then you're going to get 6xy squared plus cosine xy squared times 2y plus y squared times negative sine xy squared times 2xy. And then if you did f sub y, you're going to get 3x squared y squared plus cosine of xy squared times 2xy. And then if you do f sub yx, you're going to get 6xy squared. Let's just move the 2 out in front. So plus, okay, let's move the y out in front. Well, so I'm going to get 2y times x times negative sine xy squared times y squared plus cosine xy squared. Right? And yeah, you do in fact get that these are the same. And as we might expect, there's a general theorem. So the theorem says that, again, let's say that A is open in Rm, let F from A to R be of class C2. So we need that all the partial derivatives up through second order are continuous. Then, for each A in A, d sub k, d sub j, f of A equals d sub j, d sub k, f of A. And typically the way it's written is something like, in a multivariable calculus book, it might be written like, oh, dxk, like dxk dxj of A equals this. So that's the way I wrote it like this, is how it's written in a lot of multivariable calculus books, right? The only difference is the order in which you take the partial derivatives. Okay. And again, notice that we just required that the second order partial derivatives and the first order partial derivatives be continuous. We don't care about the third order partial derivatives, and that kind of makes sense because the statement is only about second order partial derivatives. So this theorem is sometimes called Clairaut's theorem. And the example that I gave above is an example of this. It's an example of the theorem below. And that's all there is to say about this section. These are the main results. So let's just review. We saw, well, we stated, we didn't prove it, but we stated that if you have a function where the partial derivatives don't just exist, but they're continuous, then the function is differentiable. And such a function is called C1, or continuously differentiable. More generally, you can look at nth order partial derivatives, and if all partial derivatives up through order R are continuous, then we say that f is class CR. And then there's class C infinity, and we stated Clairaut's theorem, which says that if you have a function where the first and second order partial derivatives are all continuous, then it doesn't matter which order you take the partial derivatives of, you get the same thing. So I just want to, maybe before I close, I want to mention that, we're taking this first example. This first one is the kth partial derivative of the jth partial derivative. And then this one is the jth partial derivative of the kth partial derivative. So you're taking partial derivatives of different things, right? So it's not exactly that you're doing the same thing just in a different order. It's, you're actually doing different things. But either way, you get the same thing. So if you start off with f and then take, f sub xj, and then that, the kth partial derivative of that, that's the same as taking f sub xk and then taking the jth partial derivative of that. And that's all I wanted to say in this video. Thanks.